Our speaker today is Xiong. I've known Wei for a few years. We've actually written 3 unsuccessful proposals together at this point, so I hope in future we're going to write successful proposals. Wei got he got a Doctor of Engineering from Central South University in Changsha, China, PhD from KTH Royal Institution of Technology in Sweden. He then spent time as research associate at the University of Wisconsin-Madison and Northwestern University, and since 2016 has been at the University of Pittsburgh as an assistant professor, where he's director of the Physical Metallurgy and Materials Design Laboratory. So Wei is going to talk to us today about CALPHAD, building a navigation system for materials design and discovery. So please welcome him to the Jones Seminar.
Thank you very much, Ian. So everyone can hear me clearly? Okay, that's great. All right. So I have the task to making sure that I have several slides everybody understand, and I try to do as much as I can. So CALPHAD is a name that people probably even don't know what it is. So it's calculation of phase diagrams, and I guess there's some questions coming. What is a phase diagram? So we were, discuss this layer by layer. So for the CALPHAD approach, is actually very interesting. So if you look at the definition, of course, is talking about computational thermodynamic and diffusion. So what is a phase diagram? People have to ask. Phase diagram is actually very typical used in the material science or even in the geophysics, people discussing about the thermodynamic stabilities of different phases and understanding the microstructure of different phases. And then we use this as the map, or you can say nowadays GPS, for discovering the materials, the new materials, or designing the material. So there is one saying, the phase diagram is a beginning of wisdom. So this has come from a metallurgist in Cambridge, I believe. So in order to making sure that I have enough entertainment regarding the topic, I would like to start with several basic questions. So why is it hard to find water in another outer planets? And do you like chocolate? Anybody don't like chocolate? Please. Okay, everyone likes chocolate. And then if the case, I assuming that you also like ice cream. All right? So, but then we come with a professional question. So, how to do a good design with a turbine blade? All right? So, this all link with thermodynamics. So, for example, you have phase diagram of water. So, why is it so difficult to find water in another planet? The reason is very simple. If you check, this is a phase diagram of water. So you have pressure versus temperature. And basically the energy of different phases, which one is stable. Then in this one single component phase diagram, you can identify what are the phases here. You have ice, solid phase, water, and the gas, right? So we are actually living in the Earth, and then this is a domain where you can either find 3 different phases together, but if you go to Mars, it's difficult. So this is one of the reasons why you cannot easily find the liquid water. All right. So, about chocolate. How many phases in the chocolate? It turns out 5 different phases in the chocolate. Liquid, solid. Okay. Of course, you can also include gas if the temperature is going very high. So you have the gamma phase, alpha phase, beta prime, and beta. So they have different structure. Okay. Which one is the best taste? Beta phase, all right? You look at this beta. Once you prepare these chocolates, you have to make sure you cool it down slow enough to go across the beta phase. That's a good taste you want to prepare for the chocolate, all right? So this is the reason why you save the chocolate in the refrigerator. You should not directly eat after you're taking it out. You have to place on the table for a while, and then making sure that it's annealed at room temperature and starting approaching to the beta phase, and then you can enjoy chocolate. All right? So, How about chocolate with vanilla? All right. So you actually find this typical eutectic type phase diagram. All right. So this is vanilla, solid, and then you melt, and then here is the part with chocolate. All right. So the best preparation of chocolate and vanilla is actually in this eutectic region, where you have to cool it down slowly, but then also control the mixing of chocolate and vanilla. All right. I have more discussion about these two stuff. All right. So this is just beginning. All right. So we can also find the phase diagram applying to the superalloy. So this is looking for the phase diagram of superalloy component. One contains aluminum and nickel. So this is simplified. It's a binary case, okay? But you can't imagine how hard people trying to identify this area if you magnify to here. So the gamma prime is actually a strengthening phase. And gamma is a matrix. So this is microstructure. You look at the one turbine blade, for example. You have nickel superalloy. You have to making sure that at proper composition, you have good phase component, phase fraction for both two phases. All right? So of course, real life could be much complicated. So if you're talking about real engine component, real engineering materials, not only two elements, you can end up with multiple. You can end up with more than 10. So this is a phase diagram where people study carbon content versus temperature. And if you look at one composition studying the carbon influence of the microstructure, you can identify phase stability through this calculation of phase diagrams. Okay? So then once you do the heat treatment processing, you want to making sure you hit the right temperature, right time. Okay? And then you start to do quench, forge, and then air cool, and then control the cooling rate, okay? And then you have very nice ice lab, and then you can do a lot of very fast cooling experiments for this one. And then in the end, you can actually get a very nice property of the steel. So it's very hard to duplicate this kind of steel if you don't know the genes behind this material is actually the phase diagram information. All right. Since it's very important thing, so how can we measure? So measure method, you can think about this ternary phase diagram, alumina, iron, silica. You can think about vanilla, chocolate, and sugar. It's the same, right? So you just change in the different temperature, you will have different phase appearing. So solid phase could be different with different crystal structure. If you have different crystal structure, most likely you can identify as another phase. And here we measure the phase diagram using equilibrium alloy method. You put in at the certain temperature, hold it very sufficient long time, making sure the phase is stable, and then you determine the phase boundary like this, the solid lines showing here. The red lines is actually two-phase area where you have identified so-called tie line between these two phases at equilibrium. Okay, thermodynamic properties, this is not very important thing. If you know the phase boundary is not enough, you have to making sure at each point with the composition, you know the phase transformation happens, but also equilibrium, what is their enthalpy of formation, what is heat capacity, for example. So traditionally, people will do with this. So this is a typical equilibrium alloy method. So you have an arc melter, you prepare the sample, put in pure iron, aluminum, silicon, manganese into the arc melter, and you melt them together, and making sure that you homogenize them, so you do the annealing and then quench. And then you use different characterization method to analysis this microstructure and phase, okay? So here you can also study some of the microstructure as the sulfide microstructure. And in the end, you will construct all the phase diagrams that I showed you before, and then you determine what is the complexity in this system, all right? So, in the old times, if you want to construct such a phase diagram for 3 components, we call it ternary phase diagram. This is an example. Chromium, niobium, silicon. You have to work with more than 200 alloys to determine an isotherm section phase diagram for one ternary system. And think about that. You have to work with more than 10 elements with different combination. That's terrible, okay? So of course, if your professor asks you to do this as a PhD study, you should try to refuse, all right? At least I don't ask my student to do this anymore. But it's also very important, okay? Still some ternary information is missing. So if you go to that purpose, you are not just duplicate the experiments, you still can do this. But keep in mind, this is a tedious way, all right? So people invent more effective experiments, okay? So for example, they can do diffusion couple, all right? So what they basically do, they put vanilla together with chocolate, bond them, okay, putting at certain high temperature or low temperature, and then they see the gradient of vanilla at the diffusion zone, okay? The same thing applies, okay? So if you put different elements, they starting from forming the gradient of the composition. And once you wait until the equilibrium happens, then you can actually determine the parts of the diffusion, and then you can also determine the phase boundaries, such as like this. And this is a kind of invention that people actually did for many components, okay? So they can bind them together. So for each two, you can actually determine one binary phase diagram at certain temperature. But if you do the chip junction, red circle here, then you can actually measure ternary phase diagram. Of course, different techniques have different disadvantages as well, okay? For this one, sometimes you probably end up with, the equilibrium cases is very hard to happen, and some materials have different thermal expansion, and it's very hard to bind them together, so things like that, okay? Another thing is the thing that we want to talk about today. So you actually can use a CALPHAD approach. So CALPHAD method is not a type of ab initio method. It does need to work closely with experiments, okay? So for my research, I always combine simulation, modeling together with experiment, okay? So here is the case. Once I was doing this research, aluminum nickel silicon, we have one experimentalist in University of Vienna. So he is really one of the top researcher in determining phase diagrams. So he did a measurement of almost like 12 vertical section and 10 isothermal section, if I remember correctly. So he still have trouble to identify the signal, what it tells about. What are the phase in this different area for this ternary phase diagram? So he is making the best guess for this area. So what I did is I repeat his experiments with our modeling. And then if you can get a very consistent modeling, then this is information that you're missing in this ternary phase diagram. But of course, you're not constrained with just 12 vertical section and 10 isothermal section. You can do much more. And you can extrapolate much more information, not only for the phase diagram, but also for the thermodynamic properties. Who nowadays is brave enough to do experiments on uranium, neptunium, and plutonium? So maybe not everyone, okay? We still have a lot of scientists trying to measure this, okay? So this is a collection of different data sets, okay? So if you know the CALPHAD approach, you can do a calculation of this phase diagram. And certainly, I did calculation, not the experiments, okay? So this is a calculation for uranium and zirconium. But of course, people can say, oh, you just do a curve fitting. Oh, really? So this is a very good example. If you can run a very nice CALPHAD modeling, so there is a chance where you don't need to use all the data from experiments. You can still make very, very reasonable extrapolation and prediction, okay? So my condition is you really have to be an expert and know how to do the CALPHAD approach, okay? So this is a case where I didn't use a heat capacity for these two alloys, but then I just make a prediction. Maybe this one is not easy to see, but this one is really easy to see, okay? So we have two different sets of experiments, and the CALPHAD modeling shows actually this experiment is better. So we actually find the reason of experiments, and turns out this experimental data is actually trustable, all right? So if you don't know how to do it, I know a lot of people will choose the average value, but I can tell you, usually 90% of chance, this is the worst guess, okay? So you really have to go to the literature finding what the problem there. in the literature and making your own judgment based on the experimental experience, okay? If you don't know how to do the CALPHAD approach or don't have the tool. So CALPHAD, after all, is a kind of method doing the simulation, okay? So let's talk a little bit about the models applied in the CALPHAD. And still, the best case is the ice cream, okay? So let me introduce the phase diagram a little bit more detail with this ice cream phase diagram. Okay. So you see the phase diagram showing here is very similar, like this. I just make a simplification, okay? So basically what we have is A component, B component, and here you have liquid, and alpha, beta could be different solid phase, all right? So you start have so-called eutectic reaction, okay? Liquid will decompose to alpha and beta. How you theoretically calculate the phase diagram? So basically, connecting these 2 points here is called tie line, defined for the two-phase area, okay? So what we do theoretically is trying to model the gift-free energy of each individual phase, okay? So we have liquid, alpha, and beta. And for the binary construction, you have to find the common tangent in order to define the tie line between alpha and beta. And of course, once at different temperature, then you can have different level of gift-free energy. And if you shift a little bit higher temperature, you probably end up only have liquid with beta. So these lines were showing different, but then principle is the same. Okay, so this is binary. For ternary, of course, it will be a little bit complicated, but still the judgment made in making sure that you have a clear identification of gift-free energy. Okay, but then this is a thing. You have reference state for A and B component, gift-free energy, depending on the composition mixture. And then you have the idea mixing, where, for example, if everyone's sitting here, okay, you have your own position, okay, but then you rearrange, you have another position. So this is called, idea mixing entropy, okay? So you don't move. But once you start to shake hands with your neighbor, and you start to hug with each other, then you start to create extra energy, okay? So, but then, in this case, you have to making sure that you include this excess energy. But this excess energy is very tricky. So sometimes you have to consider the shaking between these 2 people, but then he has to shake hands with him, and then I have connection with him. So this is actually more complicated, all right? But you see that he's happy, all right? Okay. So the principle of constructing the gift-free energy is actually fundamentally we want to understand heat capacity, because integration of the heat capacity will be able to derive the entropy and enthalpy. And entropy, enthalpy, then you know the gift-free energy. Okay, so this is some of the fundamentals. But anyway, so if you look at the crystal structure here, so for more complicated cases, like, you probably have different components, different elements in one sublattice of the solid phase, then you actually build different reference state. We call this end members, okay? So then you have idea again, you have access like this, vibrating interaction with each other, and then you have physics component come in. For example, you're working with a magnetic field, you're working with a high pressure field, you're working with, some external electrical field. So the CALPHAD approach actually now is a flow chart here. So what you need to get is fundamentally you have the input from experiments, but also from theoretical calculation. For example, you can calculate ab initio, okay? DFT calculation, quantum mechanics. And then you can do the measurement, but then you have to define the solid phase, liquid phase with all the thermodynamic models. And then you assign the parameters and do self-consistent optimization. And finally, you get this thermodynamic database with a gift-free energy, and then you can calculate all phase stabilities, all right? So you have a lot of conventional software and also open software available, okay? So this is one step further. After you have in the thermodynamics, you actually have to consider diffusion. Remember, diffusion is not separate. So they always have some dynamic factor which, reflect into the activities related stuff. And then you have to pull from the thermodynamics. So if you have less accurate thermodynamics, you cannot get accurate diffusion at all. All right? So they are bind together. So I usually work with thermocalc software. So this is a kind of software developed at KTH, where I graduated my PhD study. So in 1981, they have first commercial, software, thermocalc, and then they start to realize they have to include diffusion. So 1994, they include diffusion. And for the material study, even the ice study probably, you have a lot of defects and nucleation stuff. Then TC Prisma is a kind of module that you can deal with precipitation. In the material, precipitation is very important. So if you have all of this, you can control the thermodynamics, you can control the atom mobility or diffusion. Then you are ready to provide information to a higher level of physical models. So in 2011, actually, United States start with this Materials Genome initiative, okay? One very important part for studying the alloys is actually making sure that you have enough understanding of basic thermodynamic diffusion for the metals and alloys. So this is the three components they propose: computational tools, digital data, experimental tools. So I have philosophy here, okay? So we have the CALPHAD, okay? So these provide digital data. These combine with experiments, but not necessarily doing experiments. But then we also have atomistic modeling supporting this CALPHAD data, all right? But then you have to remember one thing. Doing the modeling sometimes is in a dangerous situation. You have garbage in, garbage out, all right? So you have to making sure that you talk enough with the experiment list, making sure experimental data can support your simulation and modeling, okay? All right, so I'm talking about materials design and materials discovery based on the concept starting from the CALPHAD. So what's the difference between these two terms? So a lot of people, I believe, mixing these two terms. So in the material science, at least, we deal with processing, structure, properties, and performance. So if you change the processing, you change the structure of the material, and you change the properties of the material. And then you start to influence the performance of the material. Okay? So if you discover a material, then you're actually going this way. Okay? You try to understand how the material forms in nature, and then how you get the consequence of structure and property and performance. If you design a material, it's totally different. Okay? So if you design a material, you have to come talk with your customer and asking them what type of performance they need, what type of properties they need. And then you start using your knowledge about material science to discuss about the structure they need and then control the processing. So CALPHAD basically can provide some information heavily regarding the processing and structure, sometimes can extend to the properties. Okay? So this is a typical way. If we do a materials design based on the CALPHAD approach, we list this as a systems design chart. Okay? So this actually information contains different steps of processing. This is a structure that you care about materials. It's actually the same. If you do mechanical engineering, you also care about the structure. But that structure probably is a little bit different. It's just about macro structure, okay? So you will also influence the property of this structure. And then, very important thing is you have to quantify this system design chart, okay? Just taking an example, I can say I want to lose my weight. It's also a kind of project like doing the design on my body. But the problem is I never tell my wife how much weight I'm going to lose. So I always keep the same shape, right? So which is good as well, at least can be worse, okay? So the strength is the one that you have to make sure very clear, okay? And then you go back to this column, you're making sure that what are the structure based on your knowledge, and what are the structure based on simulation or some other new findings that you can play around, okay? And then you have to do a lot of testing. You can guide the design with modeling, okay? So that's the case. This is a materials design, system design chart for ice cream, okay? So you do have a property identified, okay? So you want making sure the ice cream is not melting fast, all right? So at least you can hold a little bit longer. And then you do care about the flavor, and you're making sure that it's good looking, and then you will go and buy it for that. All right? So you care about stability. You want making sure the grain in the ice cream is not so coarse, and then lose the taste. And then you can go back, checking the microstructure regarding the matrix, regarding the ice crystals, regarding the air cells, and some fats, okay? And certainly you don't want to have the density to be very high, right? Otherwise it's very hard to bite. And then you can go back, checking the process. These are all the process. Of course, you can redesign the process according to your need, according to the facility that you are able to find. So this is the same for the microstructure evolution in ice cream. All right? So these are the typical ice cream microstructures. Okay? This I actually read from a scientific research paper. People can do this, all right? So you actually have different components in the ice cream microstructure, okay? If I don't show you the title of ice cream, you probably look at a steel structure. You don't know, right? So it looks very similar, right? So sometimes can be compared with metals and alloys. And then the interesting stuff is actually microstructure evolution in ice cream. You can also bring kinetics information in there. Okay, so you can actually check in the SEM, looking at certain temperature how the grain start course. Okay, and it's very nice to find the similarity that if you get a very coarse grains, actually the material of ice cream not considered as good. All right. So I do a lot of things regarding manufacturing, not fabricating the ice cream, but we also can utilize this for the additive manufacturing. So additive manufacturing is a kind of technique. I probably don't want to show a lot of movies, but you can easily check with YouTube, right? So it's actually layer by layer printing deposition process. And you can spray one layer of powder and start to select the geometry that you want to melt for one layer. And then after you finish, spray another layer, and then you melt, okay? So in the additive manufacturing and the alloy design at our lab, we actually identify these are all the microstructure properties we need. For example, transformation toughening, particle strengthening, and all the things identified is actually linking more or less with the CALPHAD approach. Okay, so that is the focus right now we are trying to do. And this is one example that we are developing the high-strength low alloy steel, which is very often used in Navy. Okay, so we have to making sure that all of this property match. And then we identify the structure, precipitation, and thin opinion particle. You can think about, you have particle there, and it's small enough, low fraction, and once grain boundary, grain coarsens, and it can pin along the grain boundary, constraining the grain coarsening. And then, like this M2C and carbides and copper cluster, you can actually have strengthening effects if you can control the distribution fraction and the density, number density. And here is a grain. You don't want to have the grain size to be large, okay? We're probably talking about prior austenite grain size once you solidify from the austenite phase to martensite and bainite, which is a kind of term we're discussing about steel structure. And then we want to control initial metrics, okay, regarding this, where you're starting from solidification, later melting process. But you do have the chance to restructure the microstructure during the post-heat treatment. So in the additive manufacturing, alloy design is always combined together with post-heat treatment. So this is one of the things that we have to make sure. So after we identify the system design chart, I believe right now people probably have better model compared with the modeling for the ice cream and chocolate. Okay, so we actually identify different models from structure property design, post-processing, including the post-processing structure property models and tools we can identify, and most of them are linking with the CALPHAD tool. So it's not single CALPHAD that you do calculation, but CALPHAD can provide the essential information regarding multi-component with the thermodynamic and diffusion. Then you can play with that, insert into another higher level physical model, and then you can make the prediction calculation, all right? So then we identify what are the composition design we need. And more importantly is this is a kind of busy sketch for all of the relations. But then we can also run the high throughput calculation. So you initially can put if you have enough computer capability, you can put, 1 million composition that you essentially don't know at all. Maybe you are expert, you can choose what are the area, certain range of carbon, for example, you want to control lower than 0.2%, for example. And then you start putting the initial composition, running a screening process. So basically you want to have certain property of the microstructure or certain phases. then this model can provide information here, okay? And then if you say, oh, bainite, martensite temperature, I won't control, less than 200 degrees C, then if this composition size is higher, then you exclude them, okay? Then you run the screening, and then you get the prototype design. So that's the thing, all right? You have to understand the very fundamental models, but not only in CALPHAD, but CALPHAD can provide essential information to support your prediction and design the material. But I have to say, again, garbage in, garbage out, okay? So the thing is, I do the design, but I also work with experiment, okay? So we do experiments heavily as well, okay? So in order to get successful design, so I wouldn't say this is 100% successful. We're still ongoing with this kind of research, but at least you see, I have all the instruments supporting with this experiment to calibrate the model, to verify model, to making sure the model is in a good range prediction. And then, more important thing is, knowing the alloying effects, I have better control with the composition design, okay? So these are the processes running with the design of experiments, coexisting with the CALPHAD-based modeling. Another thing I have to say, I emphasize, we do the CALPHAD for metallurgy. We can expand this area. So one example is, once I started working with additive manufacturing, I tried to help a little bit more with the modeling side. So what I do is I talk with the finite element simulation people. So what they do is they do finite element modeling, thermal modeling. They want to simulate the size of the weld pool. Once you lay the melt, you start to have the melting, okay? So these melt pool size is critical because, it determines the phase fraction and the phase properties and history of the thermal cycles of the material, okay? But then the problem is they need all of this information. This information are essentially depending on the composition of material. Unfortunately, because we don't shake hands, we don't talk with each other very often as we need. So sometimes they use constant value. So actually, some of this value you can get directly from the CALPHAD. I'm not saying it can provide digital precise, but at least you can predict something more reasonable. So here is an example. If you do the CALPHAD simulation, how should I find my mouse? I have my mouse here, okay? So this is original simulation with constant input. And this is simulation with a CALPHAD in the second column. And you can see, this is a melt pool, okay? Do you see the difference? I think the screen is large enough. You should be able to see the difference. Actually, you get simulation for the melt pool is much larger than what you have originally without considering this composition dependence if you do the finite element model. Okay. So we are running one project approaching to the end, how to shake hands more with the mechanical engineering. So we actually come in a lot of information, both from experiments calibration and original from the CALPHAD, providing information for the thermal modeling, but also for the grain texture, because for the material science, microstructure, it usually contains both phase transformation, phase stability, and grain texture, okay? So we want to make sure that we have a better model to capture the physics of 3D printing simulation. And you should remember, if you have all of this information wrong in the beginning, you actually get all the wrong results as a consequence, okay? Someone don't like the opinion. You should ask a question later. Okay, so I would like to show another interesting topic, which essentially you can ask me a lot of questions because I'm not an expert as well, okay? But I show our attempt to extend our research into the biology stuff, okay? So this is a CALPHAD approach utilized for simulating the bacterial flagella. So once I joined on Northwestern, there is a PhD student, so he has been working on this topic for a while. And we were trying to talk with each other and making sure that we have a way to describe the thermodynamics of bacterial flagella motion, okay? And then we sit together, try to identify what are the difficulties. So this is a summary of the difficulties between metals and biological systems. You have different bonding, you have different size of the system. You could get a bacterial flagella using a microscope, but you wouldn't be getting a bacterial flagella like this kind of size, okay? So temperature could be low, relatively low in the human body, but then compared with the furnace, it's still, extremely low. So for the field response, you have different, and then strains could be different. So if you look at the bacterial flagella, actually, this is a whole bacterial flagella system, okay? So we are actually interested about this filament, okay? So it turns out this filament can further decompose. Basically, this one will significantly influence the motion of bacterial flagella. So this is a running system, this is a, tumbling system, okay, running the motion. Okay, so if you cut through the bacterial flagella filament, okay, so these are the different structure, microstructure, okay? You can identify these proteins, you can identify flagellin, so these are kind of individual ones, and then you have the cross-section reviewed like this. But very interesting stuff is actually these filament actually can comparable with the martensitic transformation in steers. Because basically they have two simple units, and recombination of the single units, then you actually systematically move to another phase, okay? And then different phase have different situation, and then you actually drive the whole bacteria to move in different ways, okay? So this is the most important slide, I would like to say, okay? So you actually have proteins comparable with atoms. You have cubic, lattice structure. You can compare with cylinder shape, like the filament. And then you have the single crystal multiple forms, okay? So you can have different phases. And here is actually the phase that I'm talking about. You have different type of forms that in terms of the motion, okay? So then you go to the bulk, you have polycrystal like the material, and then you have the polycrystal with different flagella moving. So this is a units that I'm talking about, okay? You have different units, and then these different units actually only have displacement. And every change of displacement, they will end up with different phases that you can identify. So what we do is actually we have the same state variables. We have the lattice stability. So we model like what we do the CALPHAD. So the CALPHAD, as I said in the beginning, so you can actually model with a chemical contribution, pressure contribution, magnetic contribution. The same applies, so you have intrinsic flagellin, okay? So here you can model, and then you have the torque applies to flagella, and you have different pH environment, okay? And also influence the CP. So this is a stability phase diagram for each phase that we calculate, okay? So for each single diagram, it represents the stability of different flagella forms, okay? So then, you putting this together, you compare with Gibbs-free energy of different phases, and you end up with the stable phase diagrams. So at different temperature, different torque applies, and you have different type of phase for the filament. And then you actually end up with different motion effects of bacterial flagella. And then here is a thing that maybe is similar, but what I want to show is this logo Thermodynamic software, which traditionally we use for calculating the metals and the alloy phase diagrams. But now we can use it for calculating the phase diagram of filament. So you can bring things together and also extend this to the pH value, okay? So you can have the applied torque, you can have the temperature, but you can add in the pH value here, all right? So you can build another phase diagram where not necessarily apply the pressure, but apply the pH values, okay? You can get the instability or stability phase diagrams as well. And then you can further extend. So you can extend from here, PT, to the pH versus torque. And the same, pH versus temperature. So what you get is hard to visualize a 3D plot. But then what you get is torque applied versus temperature, but with different pH values. Okay? Then the motion of bacterial flagella probably ends up with different case. All right. So who is an expert in bacterial flagella? No one. Oh, you. Okay, that's good. So we should discuss. You feel free to question if this is correct or not. Maybe we should shake hands more, right? Okay. So maybe is, overemphasize this kind of linkage. But I do believe that we have a way we can bridge a lot of things together. Okay. So we have the name for the material, saying Materials Genome. There must be a reason. Of course, I agree. The genome is also, a buzzword everyone thinks is fascinating. But actually, substantially, you can also have some model described for everything, linking them together. All right? So I think you should now have a dream. Okay? By understanding some dynamics, we could have the best taste of the chocolate. And then you can take a space shuttle to explore another planet. But keep in mind, you can use one of the tools, so-called CALPHAD, calculation of phase diagrams. Okay? You should end up with this picture where you are a spaceman in the roaster. And you are allowed to take a well-designed chocolate or ice cream. But remember, CALPHAD is one of the GPS. You can identify the path to design a new material, not necessarily metals and alloys. But if you have enough information for the chocolate, vanilla, you probably also end up with a successful design with a better taste. Okay? So with that, I think you also have to expect victory. So I would like to say one more thing. So we do believe phase diagram, the beginning of wisdom. But I think by doing the research based on the CALPHAD-related materials design discovery, we feel the power of the wisdom. Okay. That's end of my slides. Thank you very much.